Hello everybody, and welcome back. In this tutorial, we're going to be covering quiz number 25, which deals with Euler-Bernoulli beams. So this is going to be the first introduction of this class into the beam topic, and as you guys will see, beam approximations, they're actually pretty easy. However, they're very, very important. As you guys will see, the approximations or the assumptions used in Euler-Bernoulli beams carry over directly into design. So some of you may or may not have taken a design class by now, but as you guys will see, for both steel and concrete, these assumptions that we determined here are used in our actual design, and they're very important assumptions. So let's jump into what those assumptions are. So Euler-Bernoulli beams rely upon three fundamental assumptions, and these are the assumptions that we use in design, and these are the three assumptions that are going to help make our lives much easier when we start talking about the approximation of beams. So the first one is that plane sections remain plane. As Dr. Sammer showed you, this is very nice because this leads to a nice linear strain profile throughout the section, and with that we can start calculating stresses. The second one, of course, is the deformations are small, and this is very closely related to the plane sections remain plane. As you guys will see in design, we want small deflections, so therefore both of these hold up quite nicely. However, if we have large deflections, things kind of get a little bit messy. Now the next one, which also relates to the first two again, is the beam is of an linear elastic isotropic material. So again, referring back to design, we always design things when they're in service to be elastic material. As you guys will see in steel, we design it to be elastic. Well, if it's elastic, therefore we can say that the plane sections remain plane, stuff like that. But the big one that you guys are going to want to remember, especially when we're talking about the approximation of beams, is going to be the Poisson's ratio effects are ignored. And that's going to be very important moving forward because it'll answer a fundamental question I know a lot of you guys will have. So let's jump into this approximation theory and see what's going on. So if we look back way from Eng 130, and you guys are thinking, Clayton, you talk about Eng 130 so much. Well, it's funny because it actually applies so much to this course, even though you don't remember. We said that if we had the distributed load Q along a beam, we can actually determine what the shear is simply by integrating that distributed load Q. And then from there, we said, okay, well, now if I know the shear along the beam, or the shear as a function of x along the beam, I can determine the moment along the beam, which was m of x. So this is right from Eng 130, and this was a fundamental part of the second half of the course when we had to do those bending and shear moment diagrams. As you guys remember, this is exactly what we did. Well, in this class, we're going to take it a step further by saying, okay, well, if I'm looking at this, all I'm doing is I keep integrating. I have Q, well, I integrate that to get V, then I integrate that to get my moment. Well, what happens if I integrate my moment? Well, if I integrate the moment and then divide by EI, or we sometimes refer to EI as the stiffness of the element, so the stiffness of the beam, we actually have the rotation of the beam. So I call the rotation theta. Theta of x is simply 1 over EI multiplied by the moment distribution along the beam. And you say, all right, Clayton, well, what if I take it one step further and integrate yet again? Well, then I get the deflection. So I say the deflection y of x is simply the integral of the rotation over the length of the beam. Now, this is kind of in its most standard form. However, these create very nice relationships, which you guys will need to kind of remember for your midterm and your final. These relationships are very simple, so I just recommend jotting them down on a piece of paper. You guys will be good to go once you guys get into the exam. And they are as follows, where the shear at any point in the beam can be found simply by taking EI multiplied by the third derivative of our deflection function. So if they give you a deflection function, which they tend to do a lot in the midterm, all you guys have to do is take its third derivative and then multiply by EI. And the same goes for the moment, but instead of taking the third derivative, we take the second derivative of moment. And if we want to go even kind of one step further, I guess one step back, depending on how you look at it, of course, we can find the distributed load along a beam if we know the deflection function, simply by going EI multiplied by the fourth derivative of that deflection function. So hopefully that function is nice, because otherwise taking four derivatives, it can be quite messy, and usually that's where all the mistakes occur. So now that we know the relationships between shear, moment, and deflection, as well as load and rotation, let's start talking about the stresses in the beam. So that's one of the things we definitely introduced in this course, was stresses in the beam, and those are one of the main interests. Now, using those Euler-Bernoulli approximations, or assumptions, we can actually define the stresses at any point along this two-dimensional beam as follows, where our stress tensor sigma has two different stress values. The first one's going to be sigma 1, 1, and the second one's going to be sigma 1, 2. So there's a stress along that horizontal direction, which makes sense. And then there's also a shear stress, and the rest are zeros. Now, if we're looking at two dimensions, it's easier for you guys to say, all right, well, the third dimension is going to be zero. Therefore, sigma 1, 3, sigma 2, 3, and sigma 3, 3 are all zero. I can kind of see that, but what about sigma 2, 2? Well, we're going to talk about why sigma 2, 2 is equal to zero. But for now, let's expand this out because, of course, I understand that there's going to be a sigma 1, 1 and sigma 2, 2, but I don't know how to calculate them. Well, calculating them is actually very easy because they have the following relationship, where sigma 1, 1 is actually negative m times x2 all divided by I. So this is very simple, even though it doesn't look like it. M, that's going to be the moment along the beam. So if I'm looking for, let's say, sigma 1, 1 at the very left-hand side of the beam, all I need to know is that moment at the very left-hand side of the beam. X2, well, that's the distance from our centroid, which in this case aligns with E1 up until the point that we want. And then we divide it by I. And the I is the moment of inertia. You guys have done this so many times with cross sections. All these parameters should be easy peasy for you guys. And I forgot that I can highlight it to show you guys what I'm talking about. Now, if we move on to the next one, which is sigma 1, 2, this is the one that's going to be complicated for most of you guys. As we can see, there's going to be 4 terms that we need to know, but 3 of which are actually very simple. So it goes negative V, and V is simple. V is just going to be the shear. So again, if I'm looking at the very left-hand side of the beam, I just need the shear at the very left-hand side of the beam, no problem. Q, I'm going to skip Q for right now because it's a little bit more complicated. If we look at the bottom, we have I again. So I is just going to simply be the moment of inertia. Comes right from the cross section yet again. And then B is the thickness into the page. So right now I have a rectangle, but of course it has a thickness into the page. That's going to be B. So V, I, and B are very simple. It's Q that's going to throw off a lot of people. And Q is the first moment of inertia. In that case, we have to find out what our x2 is going to be, and then we have to find the moment of inertia of basically the slice above x2. Now, it's hard to explain by words. However, Dr. Sammer very nicely showed you guys how this is done. It's not too bad at all, and for this quiz, we won't really need to know how to calculate Q. We'll just need to know the relationships of Q, which I'll discuss in the quiz. Now, the last thing that I want to discuss before we jump into the quiz is, again, why is sigma 2, 2 0? It's easy to see why all the sigma that involves a 3 is equal to 0 because we're looking at 2 dimensions. So why is sigma 2, 2 0? Well, this is actually a result of ignoring the Poisson's ratio effect. And as we're ignoring that Poisson ratio effect, therefore we have no sigma 2, 2. So that's why there is no sigma 2, 2. And you guys should be nice and happy because that just means that there's one less term to worry about. So if we're looking at the stresses in these beams, we only need to know about sigma 1, 1 as well as sigma 2, 2. So let's jump into the quiz so you guys can see how exactly this works. Alrighty guys, welcome to the quiz. So the quiz itself, 7 questions, but don't worry, even though that sounds terrible, the questions are actually fairly simple and straightforward, which is exactly what we want in a quiz because, well, we can actually finish it nice and quickly and then you guys can go study for all your other exams, stuff like that. So hopefully this will be a nice, short, simple quiz. I always say that it will be, but then it ends up being like an hour long, so fingers crossed, I guess, is all we'll say. So looking at question number 1, it says, the image shown below shows an I-beam that was overloaded and whose deformations violate the following beam assumptions. So we have to determine from this picture which beam assumptions it violates. So remember the beam assumptions. Part A, or I guess option A says plane sections remain plane. So that was the first assumption. Option B, linear elasticity. That was assumption number 3. Small deformations, again, one of the assumptions, or D, all of the above. So if we look at this picture, it's very easy to tell what this question will be. If we look right around the connection, so we got right there and right there. The one thing that's very obvious to see is that there is significant deformation. That steel is crippled, it's warped, everything like that. And if you guys ever felt a piece of steel, it's very stiff. It's very strong. So in order to do that, there must have been a lot of stress. So right away we can say, all right, small deformations, that was definitely violated. All right, so now we got one down. Let's look at the rest of it. Another thing we notice is that those deformations stay the same after. So the steel was twisted, stuff like that. It buckled, but then it stayed buckled. So that means that there are some plastic deformation. So option B, where it says it's linear elastic, well, that's now also violated because we have that plastic deformation. Plane sections remain plane. Well, if I were to look at that cross section that's all crippled and destroyed, Well, that's definitely not plane anymore. So all three of these are actually violated. I can say that for this question, the answer is going to be D, all of the above. Now let's move on to question 2, where we have a little bit of a different scenario, but the same type of question. So question 2 says gusset plates are used throughout steel structures to enforce the cross section. These gusset plates ensure, and that gives us 4 different options. A reduction of stress concentrations. B, plane sections remain plane. C, small deformations. Or D, all of the above. And as we're going to see, this is a very simple question. And if you guys have designed steel structures, then you guys will definitely know what these gusset plates are used for. But let's talk about it. So if we look at the beam in the picture, of course, it will have loads going down as follows. So I'm kind of drawing them in the pink. So what's going to happen at the bottom is this bottom flange of the beam is going to start making contact with the column. And from that, it's going to start transferring its stress into the web of the column. So what happens is if we look at the picture here I draw on the right, this right here, this is the column. So I'm going to put column right here so you guys can know exactly what I'm talking about. And that'd be this cross section if I were to cut, let's say, right through there. So what happens is when this flange of the beam starts to compress on the column, it's going to create a bunch of forces on the flange of the column. Now, the key here is that these forces must be transferred through the column. So therefore, they must start in the flange, but then they have to work their way into the web as such, because that web there, that is actually what carries our shear capacity for these columns. Now, when we think about the path the stress has to take to get there, well, if you guys assume that the path is going to go something like this, we're horribly mistaken. So the stress has a very hard time doing a path as such. And because of that, there will be a lot of stress concentrations around these two corners right here. So the first major thing that we do if we're designing is we're saying, okay, I don't want those stress concentrations around the corner. So what I'm going to do is I'm going to put in 2 gusset plates, and I'll draw them in, let's go a nice purple color. So a gusset plate, simply, it doesn't go all the way to the end. It goes kind of like this. And maybe something like this. So the design of gusset plates varies a lot. It doesn't really matter, but this is the basic idea. So that when we have those forces now, let's say the forces at the 2 ends, they're able to come kind of through the plate and make a nice smooth transition into the column's web instead of that sudden transition around the corner. So if we were to look at these options, it's very obvious that one of the major things that these gusset plates do is reduces those stress concentrations. So part A is a definite go. We want to reduce those stress concentrations. The reason why is because if we don't reduce those stress concentrations, we will violate the assumptions that plane sections remain plane. So if you guys go specifically into concrete design, it actually says in the codebook, if you ever have a stress concentration that's either due to a reaction force or a point load, plane sections do not remain plane. It says that very explicitly in the codebook. And then we have to actually do some advanced design, stuff like that. But because of that, we can look at this question and say, all right, well, they reduce the stress concentrations, but why do we do that? Because we want to ensure that those plane sections remain plane. And as a result, of course, we want to keep it nice, small deformations. We looked at the last picture. Of course, we don't want those kind of deformations. Those were crazy. We'd have a lot of trouble if that was our structure. So since all 3 of these are a nice check mark, we can conclude that the answer to question number 2 here is going to be just like before, option D, all of the above. So now let's jump into question 3, where we can start actually doing some calculations when it comes to beam approximations. The question 3 says using horizontal directional drilling, or HDD, an originally straight pipe with a cross-sectional area A and moment of inertia I is used to drill underneath a lake. The path of the pipe is designed such that it follows the equation below. So we have this nice equation below down here, where A naught is greater than 0 and L is the horizontal length. What is the load exerted by the earth on the pipe due to this deflection? So the thing that we have to keep in mind here is that this right here, this equation, this is the deflection of the pipe. And why is that important? Well, remember in the theory, and I kind of hinted, if we're given the equation for deflection, we can actually obtain a lot from it, such as the shear, as well as the bending moment throughout the pipe. And that's going to be very important, wink, wink, towards the midterm or final exam, because it's very easy to give you guys a nice deflection formula or deflection expression, and from there you guys can have at least 2 or 3 questions that we can use to solve for. So in this question specifically, it doesn't care about the shear or the bending moment. What it does care about is that distributed load. So remember, right from the theory, we said that, all right, well, if we have this deflection formula, the distributed load Q is simply going to be EI, and that's just fine. So we could have it in terms of EI, and then multiplied by the fourth derivative of this deflection function. So if we look at this question, it looks pretty bad, but all we're really doing is taking that fourth derivative of the deflection function. Because if we look at, all right, this EI, well, we're keeping it in terms of EI, so I can just leave that alone. So my really unknown in this equation is going to be this right here, that fourth derivative. So we're going to come down and say, all right, time to get to work. So my original expression for y of x, so this is going to be my deflection as a function of x, is equal to negative a naught multiplied by sine. And then inside the sine, we have pi times x1, but I'm just going to put x here because we only have one variable, so it doesn't matter too much to me. Pi x divided by L. So we know that we're going to have to take 4 derivatives. It gets pretty ugly, I'm not going to lie, but there are some nice little simplifications that we can do. So if we were to look at y prime, so the first derivative, we have a coefficient out in front. That's not going to change. We're going to have a naught. And then we look at sine. So when we're taking the derivative of sine or cosine, we have to keep in mind that we have to take out the derivative of what I call the baby. So if we look at this right here, everything inside those sine brackets, I call that the baby. So what we're going to do is we're going to take the derivative of that and then pull it out. And what do I mean by that? Well, if we look inside, we have pi x divided by L. So the derivative of pi x divided by L is simply pi over L. So what I'm going to do is I am going to take out that pi over L, something like this. And we know, of course, when we're also taking the derivative of sine, it changes into cosine. So we're going to have cosine now, and inside of the brackets, we're going to still have that pi x divided by L, no problem at all. So there's the first derivative. If we go to the second derivative, we're going to see that it follows the very same thing, where we're going to take out that baby, so it's going to become pi squared divided by L squared, and then the cosine is going to change to sine. The one thing that we're going to have to keep in mind, though, is when we take the derivative of cosine, we actually have a negative that comes out in front. So in the case y double prime here, that'll actually be positive. However, you guys are already experts, so I'm going to kind of skip ahead here. So the fourth derivative of y, it's actually very nice for these sine functions, and I don't know why I want x squared here, because all we're going to have to do is take out the baby 4 times. So our coefficient's going to stay out in front, nothing happens. If we take out that baby 4 times, well, then it's going to be pi squared, not pi squared, pi to the 4th divided by L to the 4th. So that's, again, just 4 derivatives. I'm taking it out 4 times. If we think about the cosine or sine, so we started with sine, we take the first derivative, we go to cosine. Second derivative would be back to sine. Third derivative would be cosine. And then the fourth derivative would be sine again. So we go, all right, well, we're back to sine, so this will be sine. And then the baby inside still stays the same, so it's going to be pi divided by L. And then we have to keep in mind about the negative that comes out, but in this case, it'll change back to negative in the end. So this is actually our answer. So therefore, if we were to want Q, it's simply going to be EI. So we're just going to leave EI all by itself. And then we're multiplying it by that fourth derivative. So I'm going to put the negative out in front. I'm going to say EI A naught pi to the 4th. I don't know why I always want to say pi squared. I don't know. All right, and we got L4 at the bottom, and this is all multiplied by the sine of pi, and I might as well make it the same as the final answer where I go big X1 all divided by L. So this is going to be the answer right here, and I don't know why I expected it to go to a bracket. It just went to a line, of course, and that's it. So all we really had to do was take the derivative 4 times. Nice, simple question. However, if you guys do not know how to take that derivative, it is not a simple, nice question. So my little hint to you guys, when you guys are in the exam, it might be nice to have a little derivative or integral cheat sheet for you guys, specifically for occasions like this. All right, guys, so that was question number 3. Let's go into question number 4, which is basically the rest of the assignment, it's question 4, 5, 6, and 7, where we start covering the stresses using these beam approximations. Alrighty guys, so this figure below is actually used for the remainder of the questions in this quiz. So question 4, 5, 6, and 7 all rely upon this figure, so I'm going to be referencing it quite a bit. It says, consider the cantilever beam with a distributed load. So that's what we have down below, no big deal. It says the beam is supported at the end where x1 is equal to 0, so that'd be that left-hand side. It says the boundary conditions are the displacement and the rotation are both equal to 0. So that makes perfect sense. When we fix something, of course, there's going to be no deflection at that end, as well as the rotation will be 0. So that checks out, I guess. It says the beam also has a rectangular cross section. What I'm going to do is I'm going to highlight this because this will be the key to a lot of these questions, as you guys will see. And it says, which point does, and then question number 4 says, the maximum von Mises stress occur. Question number 5 says the maximum positive sigma 11 occur. And then question number 6 says the maximum absolute value of sigma 12 occur. So as we can see on this beam, written in pink here, we have 6 different points to choose from. And these points are at very select locations. If we look at points B and D, they're located at the midspan of the beam, while point A and C is at the bottom of the beam, and point F and E are at the top of the beam. And as we can see, F, B, and A are on the very left-hand side, and E, D, and C are at the very right-hand side. So we have these 6 points to choose from, and we're just have to go through and say, all right, this is where the maximum von Mises, sigma 11, or sigma 12 occur at. Now, this question is kind of funny because it asks for the von Mises stress. And now, this is my opinion. You guys might think otherwise. It's actually easier to determine this question after we solve questions 5 and 6. Because typically in these kind of beams, the maximum von Mises stress will occur at the same location as the maximum sigma 11. So if we know where the maximum sigma 11 is, well then we also know about question number 4. So what I'm going to do is I'm going to save question number 4. I'm actually going to go down to question number 5 here, and I'll put it right here. And it says, where does the maximum positive sigma 11 occur? So for this, we're going to have to look at the formula for sigma 11. So sigma 11, given us from the theory, is simply negative m multiplied by x2, all divided by the moment of inertia I. So we're going to look at this formula. We're going to say, all right, well, how does this vary when we start looking across the beam? So let's look at the parameters. The first one is I. And the nice thing is, and this is why I highlighted it, is this I right here, it's constant at every point along the beam. So if I were to go up to the beam here, and I'm going to use a nice bright color to show where I'm talking about. If I were to look at this part of the cross section, well, it would have a value of I. If I were to look at this part of the cross section, same cross section, therefore it's going to have the same moment of inertia. So that moment of inertia factor will not tell us where it is because it's going to be constant throughout the cross section. So I doesn't play a big deal. Now let's look at the second factor. How about this x2 right here? So if I come up here and I say, all right, well, if x1's running right down the center, then my x2 is the distance from the center of this beam, either going up or either going downward. So if I look at this, I say, all right, I want the maximum value of sigma 11. Therefore, I want that x2 to be as large as possible. How do I do that? Well, I get the largest distance from that green dashed line as I can. So if I'm going up, the furthest distance I can go away would be up here. If I was going down, the furthest distance I could have would actually be down here. So if I were to look at this now, I can eliminate points B. So I'm going to cross out point B, and I'm going to cross out point D. Because again, I want that furthest distance from the centroid, because if I'm looking at the equation, it has x2. I want to maximize that x2. Now, another thing that I'm going to look at before we move on to kind of the final one is this right here. We have a negative out in front, but the question wants us to find the most positive thing right here, the most positive. The thing to keep in mind here is our moment, since our distributed load is going down, our moment's going to be negative, so it's actually going to counteract that. Therefore, if my x2 is going downwards, I will have a negative sigma 11. So what I can do is I can come up here and say, all right, if x2 is going downwards, I'm going to have a negative sigma 11. Therefore, point A as well as point C can also be eliminated because those two would result in a negative sigma 11 when the question wants us to have a positive. So if we look at this, there's only 2 points remaining, point F and point E. So I'm going to come down here and we're going to look at the rest of the formula. The last thing that we haven't discussed is the moment. So sigma 1,1 is going to be directly proportional to that moment. Therefore, my maximum sigma 1,1 will be the point where my moment is going to be the greatest. And we know in cantilever beams, the moment is going to be greatest at the support. And since our support is at the left-hand side, we know that point F over here will actually be our maximum moment because it's the furthest distance for x2 and it's the location of the maximum moment. So I'm going to come down here and say, all right, we said that it's going to be point F. I can come down here and say, all right, point F is actually D. I'm good to go. And now that I know the maximum positive sigma 1,1, I can actually come up and answer question number 4, where the von Mises stress. So again, the maximum von Mises in these type of problems occurs at the same as the maximum sigma 1,1. So if I look over here, I know that my maximum sigma 1,1 is point F right here. However, if you guys circle B, the answer is actually incorrect. Because if we remember what it's a function of, the maximum moment as well as x2. So if I look over here, both point F as well as point A have that maximum moment. They have the same value of x2 because they're the same distance from that center line. The only difference is A will have a negative sigma 1,1. However, if we remember that, of course, when we're doing the von Mises stress, we always have that positive value. A will actually turn positive. So therefore, point A is actually a valid answer too. So if we're looking at the question number 4 here, it's actually both A and B. Because again, that von Mises stress, it doesn't care if it's positive or negative. In the end, it'll be a positive value. So we know for part 4 or question 4, it's answer number D, which is both A and B, which is point A and F. So I guess that's kind of confusing, but I'm sure you guys get it. So I'm going to erase all these before we go to the last one. And the last one's actually pretty simple. I'm not going to erase that because I guarantee that it'll start erasing my beam. So we're going to come down here. And question 6 says the maximum value of sigma 1,2. So just like before, I'm going to write down, all right, well, what is my equation for sigma 1,2? So sigma 1,2 is going to be equal to V times Q all divided by I times B. So again, we're going to look at these along the beam. Will these be maximum at? So the first thing I'm going to highlight, of course, is these bottom parameters. So the first one's the moment of inertia I, and we said that that doesn't matter. That is the same throughout the beam. That's not going to play any sort of role when determining maximum or minimum. And the same goes with B. So remember that B is that in-plane thickness. And since that's constant throughout the beam, that'll be the same no matter which point we pick on the beam. So when we're looking at sigma 1,2, it all comes down to these two factors, V and Q. So just for fun, let's start by talking about Q. And Q has to do with the amount of area above our centroid. Now, I'm not going to go into the calculations because that's not really the point of this video. I'm going to show you guys something even better. And this will help you guys solve it all the time. So if I were to take a look at the cross section, just like this, my shear stress will always have this same form. And this is going to be the key to this. And remember this for the final exam. The shear stress is 0 at the ends, and it gets greater at the center, and then it comes back down. So the maximum shear stress in a beam like this, Tm, I guess T max, is actually always going to be at the center of the beam, at that centroid. So that from this alone, I know that the maximum shear will either be point B or point D because it is at the center of the beam. So I'm going to circle both of them. It's going to be one of these two. And that has to do with that Q factor right there. If I were to plot out Q, that's how I see that nice relationship there. So now the question becomes, all right, well, I have my 2 points. Is it going to be the one on the left or the one on the right? So now what I do is I'm actually going to look at this last term V, which is simply just going to be the shear in the beam. So if I come up here, it's very easy to see that the shear will be a lot greater at point B than at point D. So I know that my maximum shear will actually be at point B in the beam. So I'm going to come down here. The absolute maximum value of sigma 1,2, well, I said that that's point B. So for question number 6, I'm going to circle B. The reason why, again, is 1, sigma 1, 2 is a function of the shear, which we know for a cantilever beam is greatest at the support. And then the Q says that this location of maximum shear will actually be at the center of the beam rather than the two edges. So that's how I determined question number 6. So that's how to determine them just based on a beam. Calculating these parameters, we'll discuss that in question number 7. All right, to wrap up the quiz, we have question number 7, and it says, what is the maximum positive value of sigma 1, 1 equal to? So all we're going to do is we're going to take in those dimension parameters that were given for the question and substitute them into the sigma 1, 1 formula to get a nice expression. So we know that sigma 1, 1 in general form is equal to m, negative m, times x2, all divided by the moment of inertia I. Now, one thing I'm going to do, and this will just make my life a little bit simpler and take away a lot of questions from you guys, I'm just going to say this is equal to m times x2 all divided by I. And you're saying, Clayton, what are you doing with that negative? Well, we remember that if we have a simply supported beam, and I were to draw the diagram for it, the bending moment diagram, what we like to do here in Canada is draw it like this, as you guys know. But then you guys were in for a rude awakening when you guys took 372 with Dr. Yong Lee, and he drew all of his moment diagrams like this, the opposite. And this opposite case here, this green case, that's actually what's happening here. So typically what happens is this formula where it has the negative m, well, that's why we're taking a negative moment. So the negatives actually cancel. So if I were to do what I call the Canadian case, where we already assume that the moment there will be positive, well, then we'll just have it as a positive. So that's why I have the positive case here, and then the green case is the negative case. So again, the negative in the formula, well, that's if we're taking a negative moment profile, which is more American. So now that I simplified that and got that out of the way, all we have to do is create expressions for m, x2, as well as I. So if I come over here and say, all right, well, x2 is actually very simple. It's simply just going to be the height divided by 2. How do I do that? Well, let's look up at the formula and take a little peek. All the way up. So remember that our maximum sigma 1, 1 occurs at point F. So what I'm going to do is I'm actually going to erase B right there. And we know that if we're starting here and x2 is going up, we know that we want this distance right here from the center line up to F, which is simply just h over 2. So that's how I got the h over 2. Not a big deal at all. How about the second one? Well, what about if we are looking at the moment of inertia I? The question's very nice in that it says we have a rectangular section. So we know that the moment of inertia I for a rectangular section is simply base times height cubed, all divided by 12. So that's again something you guys already know. Not a big deal at all. Finally, we could wrap it up with the moment. Well, the moment's going to be the total distributed load, so that'll be the load Q times the span of the beam, multiplied by the distance from that concentrated load to the support. In this case, it's acting at the center of the beam, so we multiply that by L over 2. So this L divided by 2. So again, the L over 2, if we take that distributed load and transform it into an equivalent point load, that point load would act at the center of the beam, and therefore the distance from the center of the beam to the support is simply going to be L divided by 2. So now that I got all of these parameters, I can substitute them into the equation. So I go, all right, sigma 1, 1, this is going to be equal to m. Well, I know that m is going to be q times L, and then multiplied by L divided by 2. Perfect. And then we have times x2. Well, x2 is simply just going to be the height h divided by 2. No big deal at all. And we move down to the bottom, and that's not what I wanted to do at all. All right, let's see if this works better. Perfect. And at the bottom, we have the moments of inertia I, which is base times height cubed, all divided by 12. Well, let's be honest, this is looking pretty gross, so let's simplify this. What I can do is I can move the 12 to the top. I have q just once, so I'm going to go 12 times q. I see I got L twice, so I'm going to go L squared. And then at the end, I have an h. And we can see from the top, we have divided by 2 twice, so that's the same as saying all divided by 4. And the rest of the bottom is going to be the base times the height cubed. Now I can do a little bit of simplification here. I can say, all right, well, the height at the top will cancel out with this height cubed, and that'll turn to squared. The 12 divided by 4, well, that's just simply going to turn into 3. Therefore, my sigma 1 at that maximum point is going to be 3 times q times L squared, all divided by base times height squared. And that's it, that's all. So I'm not sure which option this is in the actual e-class assignment, but this is how you guys do it. And that concludes quiz number 25. So thank you guys all so much for listening. It's one of those ones where I said it was going to be quick, but I can see it's already pretty long. So I apologize for that. Hopefully it gets better in the future. So again, thank you guys so much for listening. I really appreciate it. I will see you guys in quiz number 26.